introduce Orlane, our speaker today, as we get a few more coming in. Really, I'm pleased to introduce Orlane Anneville. Orlane comes to us today or tonight, in her case, from France, where she is, since 2003, has been a scientist at a mixed research unit of the French National Research Institute for Agriculture, Food, and the Environment. Also with the University of Savoy, Mont Blanc. And I do not speak French, so I don't have the right sort of touch to add on those words. So Orlane finished her PhD in 2001. She did a postdoc with Dr. Strail at the University of Constance, and she analyzed synchronicity or coherence of phytoplankton community at large scales, especially thinking about the re-oligotrophication process in peri-alpine lakes. So there's a lot of course, parallels with the Great Lakes, which have undergone an oligotrophication, over the last several decades, thinking about really all the lakes except Lake Superior. And some might even say that Lake Superior has undergone an oligotrophication based on some recent work by Ben Rook, for example. So she's interested in the long-term changes of pelagic communities. She uses many different approaches: field, time series analysis, ecosystem modeling, to better understand the mechanisms driving the changes in lake ecosystems and water quality, and all the way up to fisheries. And her talk today is going to use Lake Geneva as an example of that. And I also want to acknowledge Yu-Chun Kao for the excellent recommendation for Orlane to come here and speak to us today. Orlane, I will pass it over to you. Thanks again for joining us. And you also maybe have a little bit of a chance to talk about next summer in Lake Geneva as an opportunity.
Yes, okay, so thank you for the invitation, and thank you for this introduction. So as you say, next summer we will host the Corrigonid Symposium in Thonon-les-Bains. So I don't have the dates right now, but you will get the information when we have it. And I hope many of you will be able to come to this city, Thonon-les-Bains. It's not a very big city, but it's very nice, and I hope to see you there.
That's fantastic. Yeah, it'd be really great. I know that many of the people, or some of the attendees, I think, have been to a Corrigonid Symposium in the past, if it was Bayfield or perhaps even other places in Europe. But this is the next European destination, so we're really excited that it will be there, and you'll be part of that hosting committee next summer as the details come out later. So thank you for that.
Okay, so maybe I can start my presentation.
That'd be great, thanks.
Okay, so let's go. So I'm going to talk about the long-term changes in Lake Geneva pelagic communities as a response to local and global forcing. So, cannot. Voilà. So Lake Geneva is located on the border between France and Switzerland. It's the largest lake in Western Europe, and it's deep. Maximum depth is 300 meters, and it's a warm monomictic lake. Like many large lakes, it provides a wide variety of ecosystem services. So the water quality of the lake is very important for the surrounding populations. So that's why this lake is monitored. The monitoring of Lake Geneva started in the 50s, and now this monitoring is co-funded by the CIPEL, which is the International Commission for the Protection of Lake Geneva, and it's also funded by the INRAE. It's my institute. And this monitoring takes place within the OLA observatory. So the survey was launched to protect the lake from pollution like eutrophication and to improve its management. The sampling is carried out by the OLA team, and it's a pelagic sampling. So we go on the upper basin where the lake is the deepest, here SHL2 in the figure, and we sample at this station. And all the samples are processed by the OLA team, and the data are stored in the OLA database. So these data are freely available upon request. And so we have many scientists from all over the world that come and ask this data to analyze. So we can see that this long-term monitoring is very important to better understand the functioning of this ecosystem and to evaluate its sensitivity to external forces. So during the survey, we monitor the environmental conditions. So we measure the water temperature. We have vertical profiles of water temperature. We measure water transparency, different nutrient concentrations. We also measure vertical production. We also have vertical profile of primary production, chlorophyll A concentration. We also estimate the abundance of phytoplankton and zooplankton abundance, and we estimate the taxonomic composition. We also monitor the diet of the whitefish. Unfortunately, we don't have any data on the abundance of other fish species, but we have access to yield statistics from professional and recreational fishermen. So we can have an idea of the different fish population in that lake. So like many other lakes, large lakes, Lake Geneva is exposed to various stressors, including fish management, pollution, so pollution by xenobiotics or by nutrients. We also have a lot of invasive species. The last one is the quagga mussels. So I don't know what it will happen, but I think you know these quagga mussels, and we'll see what will happen in Lake Geneva. And also we have this habitat and climatic changes. So there are a lot of pressures that have an impact in the communities and the environmental condition of the lake. So as an example here is water temperature. So here in this figure, you can see the annual averages of water temperature measured in the first 10 meters. And since 1973, you can see an increase in water temperature. So the lake is warming. But I want to show you also this figure because I think it's important when we study the biology. It was a study made some time ago, and we focus on different seasons. So we have water temperature for different seasons. And if we look at the summer, for the period between 1972 to 2008, we did not see really a warming of the lake. We have oscillations, but no real increase in water temperature. And this result is coherent with the result by Orlane et al. In that paper, we showed that the lakes were warming at the global scale, but we showed that the warming rate was different between the lakes. And in this study, the warming of Lake Geneva was not significant. And it was not significant because we focused on this summer season. Now, if we look at the spring, for example, we can see a shift here in 1988. And we can clearly see two periods, a cold period, which is associated with a negative phase of the North Atlantic Oscillation. And we have a warm period, which is associated to the positive phase of the North Atlantic Oscillation. And this North Atlantic Oscillation has been identified as an important driver of meteorological conditions in Europe. And many papers show that the North Atlantic Oscillation had a strong impact on water temperature in European lakes. So this is coherent with what we can see in other lakes of Europe. We also see a change in the duration of the period of stratification. So in this figure, you have the number of days of the stratified period, and you can see an increase of the stratified period because the stratification occurred earlier and it end up later in the year. So we have important change in the thermal dynamic and thermal characteristic of Lake Geneva. An important change in Lake Geneva is a change in its trophic status. So in the 50s and 60s, because of an increase in human activity in the watershed, we have observed an increase in phosphorus concentrations measured in the lake. This increase in phosphorus was accompanied by a decrease in water transparency, the decrease of whitefish and Arctic char, and also we had the occurrence of phytoplankton bloom. So there was a real need to reduce phosphorus inflow into the lake, and different measures have been taken. So they built some wastewater treatment plants with the process to remove the phosphorus. And also in Switzerland, they banned the detergent containing phosphorus. And as you can see, all these measures have been very efficient, and phosphorus concentration switched from 90 micrograms per liter in the early 80s to now around 15 micrograms per liter. So we have a real oligotrophication of the lake and an important decrease in phosphorus concentrations. So all that changes had an impact in the biological community of Lake Geneva. And here we are going to see what happened with the fish community. So in these figures, you can see the catch per unit effort of different populations. And you can see that the trends are different depending on the species. Some species are increasing while some other species are decreasing. So to better illustrate the trends in the fish community, we ran the PCA, the principal component analysis, and we see that the first axis of the PCA is mainly explained by the pike and by the whitefish, and the second axis is explained by the Arctic char and the perch. So now if we plot the years within this first plan, we can see a nice temporal trajectory, and the more recent years are characterized by high abundances of pike and whitefish. So then when we try to understand these trends and we correlate the scores of axis 1 with phosphorus concentration, we see a significant correlation. So we can say that this trend in fish community is mainly due to decrease in phosphorus concentration, so to the oligotrophication. So now let's focus on the whitefish population. So here in this figure, you have the catches of whitefish. And you can see that when the lake was very eutrophic, during the maximum of eutrophication, the catches of whitefish were low. Then we see a first increase in the 90s. Then we have a plateau, and then we have a second increase, a spectacular increase here. So we have made different studies to explain these trends in the catches of whitefish. And here I don't have time to present the results of each studies, but I'm going to present you a synthesis, a resume, as a conceptual model to explain the trends in whitefish in Lake Geneva. So first, as you know, whitefish spawn on the ground. So the eggs are very sensitive to the oxygen concentrations. And in eutrophic lake, we don't have good egg survival because we have anoxia often on the sediment. So the trophic state of the lake is very important for the rate of success of reproduction in whitefish. So in Lake Geneva, with a decrease in phosphorus concentration, we had an improvement of the spawning area. And so we had a better egg survival, the first thing. Then we have seen an increase in water temperature, and we have made some studies to analyze the link between the water temperature and the larval growth, the whitefish larval growth. And we can see that the whitefish larval growth is strongly dependent on water temperature. Actually, when it's warm, the larvae grow faster. So in Lake Geneva, with the warming we have observed after 1988, we probably had larvae which grow faster. And when the larvae grow faster, then we may have a better recruitment because they are longer sensitive to predation by the other fish. And also, because of warming of Lake Geneva, we have observed a change in the phenology of the zooplankton. When the lake was warmer, the zooplankton developed earlier, and we had a better match between the hatching of the whitefish larvae and the zooplankton bloom in spring. So in warm year, we have whitefish larvae which occur in a lake where the food is already here and where the temperature is warm. So the larvae can grow faster and we have probably a better recruitment. So a better egg survival and better recruitment explain the first increase in the whitefish abundance. Then the environmental condition remains good. And in 2006, we had an exceptional year with a very strong cohort. We had a very high abundance of cyclopids in spring. So cyclopids is important for the larvae of whitefish because the larvae at the beginning start to eat copepods. So we had a very abundant copepods. We had Daphnia. We did not have many perch. The perch can be a competitor, or perch also can prey on the larvae and the young whitefish. So we didn't have a lot of perch. And we had good condition, and we had a very important cohort. It was a very strong cohort, and the fishermen were not able to harvest all these fish. And so the years after, we had old individuals. So we had old spawners, which are more fertile. We had good environmental conditions, and then it explained this second increase observed in the more recent years. In parallel of this change in the whitefish community, we observed an important decrease in the abundance of Daphnia. So here you have the annual abundance of Daphnia since 1974. And Daphnia is a very important species for the fish because it's an important prey. So we ran mixed model, and the results say that this decrease is due to the increase in whitefish abundance because we have a higher predation pressure on the Daphnia. Other colleagues have analyzed the size of the Daphnia, and they showed that the size decreased. And this decrease in the size of Daphnia can also indicate a stronger predation pressure by fish. So these results are coherent. There is another hypothesis to explain this decrease is lower food quality. Because of low phosphorus, we expect also phytoplankton with lower quality. And it's some colleagues from the University of Geneva who are working on this hypothesis. Now, if we look more carefully at the phytoplankton community, so here you have the Bretum index, and it's an index we are using to assess the ecological quality of lakes for the European Water Framework Directive. This index is based on the taxonomic composition of the phytoplankton. And you can see in this figure that with the re-oligotrophication of Lake Geneva, we see an improvement of the ecological quality of the lake. That means that in recent years, we have more phytoplankton species which are characteristic of oligotrophic lakes, and we have less species which are usually observed in eutrophic lake. So this is good. The water quality of the lake is improving. But if we look at the abundance, the total abundance of phytoplankton here, you don't see any decrease in the abundance of phytoplankton. And some years you can observe the bloom of some filamentous species, which is Mugeosia gracillima. So we have tried to understand these trends in phytoplankton. Why does the phytoplankton does not decrease while there is less phosphorus? So we ran different statistical methods, And we have identified some phytoplankton assemblages with a method based on the Bayesian probability. Over the 400 phytoplankton species observed in Lake Geneva, we have selected 34 taxa that represent 80% of the total phytoplankton biomass. And over these 34 taxa, we have been able to identify 5 phytoplankton assemblages with the assemblage A1 in light gray that represent or that explains 83% of the total variability of the phytoplankton biomass. So actually, this assemblage A1 captures very well the interannual variability of the phytoplankton community. So identifying the drivers of A1 should allow to explain the long-term changes in total phytoplankton abundance in Lake Geneva. And to do so, we use a method which is the convergent cross-mapping. It's a nonlinear method to determine the causality. So this method is very interesting because it is well adapted to address the 2 main issues in data analysis. The first issue being that correlation does not imply causation. And the second issue is that no correlation does not mean no causation. So we use this method, the CCM, to quantify the causal interaction among the drivers and the phytoplankton assemblages. And for the drivers, we have tested the solar radiation, the water temperature, phosphorus concentration, and the Daphnia abundance. And this method helps us to identify the direction of the causation. In other words, we wanted to see if we had a top-down or a bottom-up control. So this is the results of the CCM. So we get this causality network. So here you have the drivers, the Daphnia, phosphorus, solar radiation, temperature, and you have the assemblage A1 of phytoplankton. The arrow indicates the direction of the causation, and the thickness of the arrow indicates the intensity of the causation. So we can clearly see that the phosphorus concentration is a main driver of assemblage A1. So decrease in phosphorus induces an increase in A1. So this might be strange, but it's coherent with previous results. And actually in Lake Geneva, with the decrease in phosphorus concentration, we also had a change in the vertical profile of the phosphorus concentrations. So here is an example. So here are the years, and the axis, the ordinate is the depth, and the color is the phosphorus concentrations. And you can see in this figure that the low phosphorus concentration are reaching, are going deeper and deeper. So we have a deepening of the phosphorus depleted area. So in the last year, we have almost 10 or 0 microgram per liter of phosphorus till more or less 100 meters sometimes, while before it was just till 50 meters. So we have a deepening of phosphorus depleted layer. Another way to represent this phenomenon is this figure. So here you have the months, and here you have the years, and here the color indicates the depth of the phosphorus depleted layer. So when we were at the maximum of eutrophication, you see that the depleted layer was around 10 meters, so it was not so deep. And in the end of the 90s, we did not have any phosphorus till 30 meters. So we have a deepening of this phosphorus depleted layer. And this process match, not process, but this trend match very well with the occurrence of phytoplankton assemblages 6 here, which is actually our phytoplankton assemblages A1. And this assemblages is made of what we call the disturbance tolerant R species, like Diatoma tenuis, Mugeosia, or Planctotrix rubescens. There are species which can grow under low light intensity. So this species actually can grow deeper in the water column, where there's not many light, but where phosphorus is still available. So we checked the vertical profile of the chlorophyll A concentration, and we compare the profile between different periods. So when the lake was eutrophic and when the lake was less eutrophic. And you can see that when the lake was the most eutrophic, the maximum of chlorophyll was around 5 meters, and then it was more around 10 meters. So we can clearly see a deepening of the phytoplankton. And this deepening of the phytoplankton match with the occurrence of the assemblage A1 that is made of species adapted to grow deeper in the water column because they are light adapted, and they can use the phosphorus where it's still available. So other drivers of assemblage A1 is the solar radiation and water temperature. It is also coherent with previous analyses we have done. And the interesting thing in this study was that we were able to show that Daphnia is also a driver of the assemblage A1. And if you remember, the Daphnia abundance in Lake Geneva is decreasing. So actually we have less grazing pressure on A1. And this is the link. So to resume, in Lake Geneva, we have a decrease in the abundance of Daphnia. So we have less grazing pressure on the phytoplankton. And so we don't have a strong control on phytoplankton abundance. So we have this increased phytoplankton abundance. The decrease in Daphnia is due to the increase in whitefish and the stronger predation pressure on Daphnia. So we see here a nice top-down control, actually, and the whitefish has an indirect effect on the phytoplankton. And it's here that the paradox of a re-oligotrophication comes, is that the increase in whitefish is due to the increase in temperature, but also is due to the decrease in phosphorus concentration. So that is the funny part in this story. It's the paradox. Now we can see that the Daphnia abundance are very low, and we have a lot of whitefish. So we could expect a negative feedback. And interestingly, not for the fishermen, but for us, we see in more recent years an important decrease in the catches of whitefish. So we are now working to try to better understand why we have a decline in the whitefish. And we have two hypotheses. First, it's because of a lower reproduction success, or second, it's because of a lower recruitment success. So we have started by investigating the second hypothesis, and we use the scalimetry to do so. So we analyze the scales of whitefish in Lake Geneva, and we try to identify the environmental factors that drive the rate of growth of the fish during their first year of life. So they are larvae and juvenile. And during this first year of life, the whitefish growth is very sensitive to water temperature in spring. Warmer water induces faster growth. It's not surprising. We also showed that the abundance of Leptodora in autumn has a positive impact. So the more you have Leptodora in autumn, the faster the fish will grow. Also, the abundance of food in spring is important. So abundance of food is copepods and Daphnia. And we have seen a negative effect of water temperature in autumn and summer. So warm temperature have a negative effect on the growth rate of the young whitefish. So now if we compare the values of these different drivers between different periods. So here it's the abundance of Daphnia for the periods when we have strong whitefish cohorts. So the first box plot, it's when we had a high abundance of whitefish. And the last box plot, the last box, it's when we have a decrease in the whitefish abundance. So we can see that when we have a decrease in whitefish abundance, we also had less abundance of Daphnia in spring. when we have this decrease in whitefish, we had warmer temperature in summer, and the low abundance of whitefish match with lower abundance of Leptodora. So in conclusion here, we can see that we have some changes, environmental changes, which are expected to reduce the larvae and the juvenile growth. So maybe it can reduce the recruitment success of whitefish, and it may explain why we see a decrease in the abundance of a stock. If we do the same analysis, but we study the drivers of the growth rate during the second year of life of fish, we see the effect of Bytotrophes. The presence of Bytotrophes led to faster growth of the whitefish, and we also see an intra-specific competition. So it seems that the food abundance is an important driver and may explain the decrease in the whitefish. So we looked for other evidence for food limitation, and we use the stomach content, the survey of the diet of the whitefish. So these are fish caught by professional fishermen. So they are adults, they are 2 or 3 years old fish. And we have 1 sample per month. We analyze 10 fish, and we identify the taxonomic composition of the prey, and we estimate the contribution of the prey to the total biovolume. So we have information on the diet, on the seasonal succession, and on the interannual variability. So in Lake Geneva, the whitefish eat Daphnia, Bytotrophes, and Leptodora. These are the main prey. We can see clear seasonal pattern. So here is an example. So the months and the contribution of the different prey. So you see that in spring, the stomach content is made almost Daphnia. Well, the Daphnia abundant prey in the spring. Then the whitefish switch to Bytotrophes, and then they eat some Leptodora. So we have this clear seasonal pattern, but we have interannual changes in this seasonal pattern. So here you have the temporal map that shows the contribution of Daphnia, Bytotrophes, the month seasonal, and along the year, so interannual changes. So you can see that the Daphnia is the main prey during spring, but in last year, you see that the Daphnia seems to be less abundant in the stomach. In contrast, Bytotrophes is the dominant prey during summer, and you can see that since 2014, Bytotrophes is also very important during spring. And we see a significant correlation between the contribution of Daphnia to the diet and the abundance of Daphnia in the lake. So when you don't have much Daphnia in the lake, you have less Daphnia in the stomachs. So it seems that the whitefish adults are now switching to Bytotrophes in spring. So this is good to the adults. They can switch because there's perhaps not enough Daphnia, so they switch to another prey. So the adults can do that, but the whitefish larvae are probably too small to switch to this large prey. So low abundance in Daphnia in spring might be a problem for the whitefish larvae and then for the recruitment. And if we looked at the abundance of the different zooplankton taxa in the lake, you can see for the cyclops, so it's an important food for whitefish Daphnia. Well, the abundance of cyclops is decreasing, and we can see also a decrease in the abundance of Leptodora and a decrease in the abundance of Bytotrophes. So it seems that whitefish has a problem with food abundance or food availability in Lake Geneva, and perhaps also, especially during spring, for the whitefish larvae, which may have problem to find enough Daphnia. So this might be an explanation, but we have other hypotheses. Perhaps we have too warm temperature during summer or winter, or there may be the effect of other parameters like fishing pressures. So we are still working on that, and we have recently hired a PhD student, Fabien Bourinet, who is now working on this question. So we are expecting very interesting results very soon. I thank you for your attention, and I thank you all the colleagues who have contributed to the different studies I have presented.
Thank you very much, Orlane. Fascinating talk. I loved how you went all the way through the ecosystem, from nutrients to phytoplankton up to whitefish. So you do have some time. I forgot to check with you before. It's okay if we have some time for questions.
Yes,
so we
yes,
can
yes.
do that. We can do that through either raising your hand and I'll call on you, or you can also put questions in the chat. Just a few points, especially for some of our Great Lakes audiences. So your whitefish are pelagic as both adults, right? Which, yeah. Whereas ours are benthic. So that's an important.
They are all pelagic. They are all pelagic. Yes.
And,
now it seems that we just have one species. Before we had two species, but they have disappeared because of overfishing, perhaps also because of stocking, because of eutrophication. Well, they may have several factors that can explain the disappearance of these two species. And at that time, to maintain a stock, people bring fish from different parts of Europe, from Poland, well, from different countries, and also many from Lake Neuchâtel in Switzerland. So now that kind of fish is between all the different sources, but it's more or less similar to the whitefish we find in Lake Neuchâtel. But yes, and it's just pelagic. So it's pelagic, but it's spawned in the littoral. So when you walk around the shore in winter, you can see the spawner. So they will spawn near the shore.
Okay. So are they spawning? They're spawning in late fall, winter, shallower waters, and their eggs are overwintering and hatching in the spring. Is that right?
Oops, the connection was not good, so I'm not sure to have listened the question correctly. But they are spawning in December. So they spawn in December, and then the larvae hatch in March, end of February, March, and during the spring. Yes, the period of hatching is more or less long. It depends. It's their winter spawner.
And is there still stocking going on, or has stocking now ended?
Oops.
Maybe I'll try it again. Are you having a hard time hearing me? Let's see, Nick, is it just me that's frozen, or is Orlane frozen?
I can't hear her, but your video just cut out. Did you do that on purpose, or?
Yeah, I was trying to see if it was my bandwidth.
Oh, yeah, I wonder if we just lost her. Yeah, she, I think, just dropped off.
Okay, I think she'll come back.
No, she's still here. Orlane, can you hear us?
So while we wait for her to rejoin, it was just sort of, I know we have a big Great Lakes audience, just emphasizing some of the differences between the European whitefish and our Great Lakes whitefish. Theirs are more like our Cisco's, but a lot of interesting parallels. And just building off of the talk Kimo Kahalian gave a couple of months ago, talking about the divergence of whitefishes, which would be analogous to the differentiation of our Great Lakes Cisco's. Sounds like they only have one whitefish species in Lake Geneva, and that it was brought back through stocking through another Switzerland lake. And I was asking her if they're continuing to stock or not. Let's see if she's going to be able to rejoin us.
So she just sent us an email saying that she lost her connection. So I'm gonna try and help her troubleshoot. Looks like Jason Stockwell just responded to your question.
Yes. And then I don't know, another question, large hatchery right on the shore. So another question, I think, did she mention that they have dracaenid mussels there now, quagga mussels? I thought I heard that, but she didn't bring that into our talk. Perfect. Thank you, Jason. Jason does think they have recently arrived in Lake Geneva. So another parallel, they have Bythotrephes. A lot of common players that we see in the Great Lakes.
It looks like Orlane was able to rejoin.
Yes,
Are you
I'm
there?
here again.
Excellent.
Welcome back. I guess the final question that we had, just for clarity, Orlane, is could you talk a little bit about the stocking component of the whitefish? How much stocking is contributing to the adult population, and if it and how much continues to be important, or are there plans to scale it back?
Yes, so during the eutrophication of the lake, we think that stocking was very had an important impact because it allowed to maintain the population. But now with the first increase, the fish were able to reproduce themselves on the lake, so the stocking was not so important actually. But they used to do it because for the fishermen liked and prefer to stay with the stocking, and they can go and fish during the winter. They can fish the genitor during the winter, so they can sell the fish during winter. So like to maintain this stocking. So we are still stocking, but it's not so important now.
Okay. Thank you. Well, let's go to our first hand raised, Elvita.
Yeah. Hey. Great talk. A lot of phytoplankton, which I like. That's kind of my field. I have more comments and questions. One comment, when you show the graph with the long-term temperature changes, I didn't see reflection. It was so interesting that like summer and winter didn't show any changes, and then spring showed the temperature increase. And maybe you can comment on that, like why you see so distinct. Like if what I would think, if there is a long-term temperature increase, then maybe that will be reflected also in the winter, because like winter didn't show any temperature changes. But maybe there's something else which I didn't kind of catch up. And then did you ever consider to also look at the jellyfish? Do you have a lot of jellyfish? Because this is also a very important player. And I think like in lakes, which are kind of warm lakes, this is a very important like predator on the Daphnia and other zooplankton species. So, and then this connection between Daphnia and Bythotrephes, there are some concerns that Bythotrephes might graze on Daphnia too, and maybe that's why the Bythotrephes, the species, you know, get more kind of abundant and more important food source. Yes, thank you.
Yes, so I understand the comments on the temperature, but I want just to give more information. Now the temperature is increasing even in summer. We can see also an increase in winter, and so because whitefish is a cold fish. Yes, whitefish is a cold fish. Warmer temperature in winter is a problem for the reproduction and the egg survival. So we want also to explore this hypothesis of warm temperature during winter that may have a negative influence on the egg survivals. Regarding the jellyfish, we do have some jellyfish in Lake Geneva, but they are very rare. And it seems that they are just in the littoral. So I don't know how it is in your lake. But in the pelagic, we have never observed the jellyfish. It occurs sometimes in some ports, but it's very, very rare. And then regarding the interaction within the zooplankton community, yes, for sure, I think there are interactions. Some zooplankton are eating the young Daphnia and whatever. So yes, I think it's also interesting to investigate that happens.
Great, thank you. Okay, so it's new. So it's good to know that you don't have so much jellyfish, because in the Baltic Sea, it's a big thing and it very much affects the zooplankton composition seasonally with the jellyfish biomass. That's why. Yeah. Okay.
Thank you. Good question. I'll take one from the chat from Serena Lake. She asks, is there concern that Phytoplankton are not as nutrient dense as other zooplankton for the juvenile whitefish and therefore limiting or affecting recruitment? So if you just look at their lipids or their energy content relative to other zooplankton, could that also be a concern? She was wondering if you've looked at that at all.
Yes, so I think, yes, we can have some interaction and control of zooplankton, but we did not investigate yet this interaction. So I think it's something that can be done.
Okay.
And then there is something with the mussels also, I think.
Yeah, Ellery Morano. Yeah, can you read that? She's asking about.
Yes. Geneva. Yes, so we are just starting some studies on the mussels, and we are starting by trying to see the extension of this mussel, and they are extending very quickly. And there are some projects to start to see if it has an impact on the diversity and on the things. In Lake Constance, they have made a nice studies where they show that it has an impact on the fish, the prey of the fish, and what fish are eating, well, the source of the carbon. And I think we can also do this in Lake Geneva, but actually I'm reading a lot of things from the Great Lakes, because you already have these mussels, so you have experience, and we will take inspiration of all the work you have done there, because I think it will be a very important problem, and also for the water, use of water for drinking water. Well, yes, it might be a problem, and it may have a very important impact food web and Lake Geneva. So it's an important question, and but we cannot prevent this invasion anymore. The mussels are here, so I don't know if there is a solution to do something. But if you have an idea, if you have a solution, please let us know, because yes.
There definitely is some research and development at small scales to try to limit their spread, or to make local, removal efforts. Okay. There's a Pseudomonas bacteria that can be toxic to them, but it's very difficult to apply in deeper waters and at large scales. Yeah. But yeah, I think there's a lot of motivation as more of these mussels invade and alter the food webs fundamentally and have effects on productivity that ultimately cascades up to fish. That is a concern here, and will sadly face you all in the future, probably. While I wait for another question, one thing that caught my eye looking at the zooplankton data, Orlane, was the high numbers of cladocerans you had in the spring. something we see in the Great Lakes are mostly calanoid copepods. We don't see as many cyclopoids anymore since our lakes are less productive, but we generally don't get our cladoceran blooms until summer. But you're showing Daphnia as being important in the spring. You also showed Bythotrephes being an important prey item in the spring. And that's just something very different than what we see in the Great Lakes. So I thought that was interesting. And I wondered, I mean, first of all, is Bythotrephes native there, or is that another invasive species? Do you know?
It has been imported, so maybe we can say, but now it is native. But it has been, yes, it was not here at the beginning.
Okay.
And yes, I think it's interesting to see the seasonal pattern of Daphnia and Bythotrephes, because with climate change, I think we may have changed this seasonality and the date of the blooms. And also if there is a strong predation pressure by fish, also I think it can change this seasonality. So I have, during my PhD, I analyzed this seasonality, but I did not update this analysis, and but we can see some change, but cannot explain exactly why.
Yeah, climate change may be a good explanation. I don't know if we have other zooplankton experts from the Great Lakes on the call that wanted to weigh in on that, the seasonal differences in cladocerans that caught my eye. But. See, are there hands I don't see up yet? Questions from the chat? One other common thing I noticed is that we're beginning to do more and more sort of larval lake whitefish work in the Great Lakes. And some of the studies that people like, well, Ed Rutherford and others have looked at is showing that cyclopoids are important for larval lake whitefish in the Great Lakes. So I thought that was another interesting sort of common result. And again, we're thinking very much about that potential mismatch in prey for declining lake whitefish in the Great Lakes. And so it's interesting that your research has shown that the warming climate has actually improved, I think you said improved the overlap between zooplankton and emerging lake whitefish larvae. And so we're thinking about trying to get better data on that. Of course, we also have mussels, we think, that are influencing clearly the phytoplankton in the spring by filtering out. We've lost a lot of our spring phytoplankton bloom because of mussels. And we are just now beginning to try to get a better idea of what effect that has on spring zooplankton, especially in that near shore where the whitefish are hatching out. So,
yes, I think it's important because it's true that our zooplankton is from the middle of the lake, so we don't have the clear image of what happened near shore. So we make the hypothesis that the trends are the same, but maybe, and with the mussels, the things will be very different. And I think we should also monitor this littoral zone and see better the zooplankton dynamic. And yeah, I think
okay. Yeah, we could talk to you more about some of the efforts in the Great Lakes to do more of that near shore littoral monitoring that like you, we didn't have historically. Most of our lower trophic level monitoring was in the offshore, just like your site was. Ellery, you had your hand up. Did you want to ask a question of Orlane?
Hello. It was kind of a follow-up to the quagga mussel question that I had earlier, and I was going to mention how I've read that there's a pretty large consumption of the spring phytoplankton bloom by the invasive mussels, but then Bo went and said that, so it kind of I kind of said what I was going to say, but and I thought maybe that could be a possible difference, but I'm sure there are quite a few differences. But I just wanted to say thank you for your very interesting talk, and I really appreciated going through all of the different aspects of the lower trophic levels. I thought it was really interesting.
Yes, thank you. I didn't hear the question, so I just hear some parts. Also interesting talk, so thank you. And yes, sorry, my connection is not good.
Yeah.
Okay, Bo just said what I was going to say is all. Thank you.
Thank you.
She was complimenting your talk, Orlane. So any other questions? Okay. Well, I mean, it's hard over internet. It's hard when connections can go in and out sometimes, but I think there should be an option in your reaction to give a hand clap to just express your appreciation for Orlane joining us and staying late. Very different time zone. We really appreciated your perspective, and it's fascinating to learn more about different systems that have many common challenges to our Great Lakes. And we hope to see you in person. You're not coming to JASM, is that right, Orlane? You're not able to come to
No.
Grand Rapids. Yeah.
No, I cannot come this year. Perhaps next year, I hope. And
I know-
I'm waiting for you for the Corrigan Symposium last year.
Very-
So
Very good. And we know that you also attend IAGLR on some occasions too. So that's another chance you would have to meet Orlane. Oh, Edward, Michael. Oh no, sorry, you were clapping your hands. I thought you were raising your hand. So very good. All right, well, thanks again for joining us, and we
Okay.
hope to see everybody next month.
Thank you very much.
Okay,
Bye.
thanks everybody. We'll see you May the 6th, right, Nick?
Yep,
So-
May 6th.
Okay, thanks again, Orlane.
Thank you, Orlane.
So yeah, we have a basically a beach seining program, Orlane, where we go out and are sampling for whitefish larvae in a meter or two of water with like a 500 micron mesh seine. And we also are pulling a zooplankton net to try to see what that zooplankton environment is like for those whitefish larvae as they hatch. Something that we've just started within the last 5 or 10 years. We don't know yet if it's going to be indicative of year class strength or not, but it does speak to that mismatch that we have with regard to most of our zooplankton and phytoplankton and nutrient sampling is offshore, and we don't really have much near shore. So.
Mallory, did you have your hand up?
Yeah, I'm sorry. I just have another question. Sorry. I was just wondering if you had ever found, or if you had looked at the diets of larval fish, and if you had found that they were eating larval mussels at all. That was just something I had observed when I was doing my master's thesis, and I was just curious if you had seen that ever.
You hear me? Okay. Bye.
Ellery, you could try just emailing her.
Yeah, I think I should try that.
I think with the connection, it's just, it's too hard to
Right.
have a conversation.
Yeah, I imagine a transatlantic connection is very difficult.
Mm,
Okay, all right, well,
all right.
thanks again, Nick, for organizing.
Mhm.
Thanks,
Yeah.
thank you, Eugen.
Right. Thank you, Bob. Yeah, I was about to ask you a question.